Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. Okay, let's think that we have 2 points because we're going to do a rate of change. We have our point P and our point Q, and we want to know the average rate of change. Okay, the P is going to be at an x comma f of x, and Q is going to be at a comma f of a. Now, because we have 2 points, this is a secant line, so the average rate of change which would be like, you look at where you start and your finish and how many miles you went and how long it took you, about how many miles per hour did I go. That's your average rate of change. It's also known as the slope of your secant line. And to do that, we'd have y2 minus y1 over x2 minus x1. Okay, what if, though, I moved P closer and closer and closer and closer and closer and closer to Q? What if this x value was almost that a value? We'd be getting closer and closer and closer and closer and closer to a single point, which means we'd be getting closer and closer and closer to the instantaneous rate of change, which would be the slope of your tangent line. So A has to get closer to X, or X has to get closer to A, right? So this would be a limit as X approaches A, or they approach each other, right? However you're looking at it, of f of a minus f of x over a minus x. You could also do it, and the limit as x approaches a of f of x minus f of a over x minus a. They're going to get the same result because a positive divided by a positive or a negative divided by a negative, however that works. Okay. So let's think about that. Let's look at y equals 1/2 x squared. Let's make it a little, we'll go with y equals 1/2. Okay. I want to know the slope of the tangent line when x equals 3. Okay, well, okay, at 3 we're right there. So it's not super flat, but it's not super steep. It's getting ready to take off, right? But it's definitely an uphill slope. So we could we know at 3 we're at 4.5, right? And then we want to be at 3 plus a little bit. We don't want to be very far off of 3, and we don't care whether we're bigger than 3 or we're less than 3, correct? So this would have to be 1/2 3 plus that little bit squared. Okay, so now we have our 2 ordered pairs. the one where we want to be at and the one close to where we want to be at. So we want the limit is h is almost nothing, right? We want h to be as tiny as possible. 0.000000001, right? And then to do the slope, we'd have to do this minus this over this minus that. y2 minus y1 over x2 minus x1, right? And because we want the slope of the tangent line, we have to do that limit. We want to go from 2 points to 1 point. And the only way to go from 2 point to approximately 1 point is to make them on top of each other. All right, so I don't want to deal with fractions a lot, so I'm going to go ahead and multiply by 2, but I'm also going to cancel this out. So that'll give me 3 plus h squared minus 9 all over 2h. I think that makes it a little bit simpler, right? So then we'd have the limit as h approaches 0 of 9 plus 6h plus h squared minus 9 all over 2h. And then we'd have the limit as h approaches 0, the 9s would cancel out. And I would have 6h plus h squared divided by h. They all have an h in it, so I'll factor out an h, which should leave us 6 plus h divided by 2. Now I can finally substitute 0 in, and I get 6 divided by 2, which is 3. Well, let's check. Okay. Well, slope of 3, right? So 3x. It may not touch at that point, but let's see. Yep, almost. So there we go. They're meeting at 3, 4.5, right? They have a point of tangency in common. And we can see that that just brushes the graph and continues on. We will eventually come up to the equation of the tangent line. We're just looking at the average rate of change and how it gets us that instantaneous rate of change. So we now have a rule, okay? We kind of developed it. We know that when you have two ordered pairs, A, B, f of A, f of B, the slope of your secant line is f of B minus f of A over B minus A. What happens when we switch this up to x and x plus h instead of A and B? We have the limit for the slope of the tangent line. We want those super close together, right? The limit as h goes to 0 of your y2 minus your y1 over your x2 minus your x1. What's going to happen to that numerator every single time? Or not the numerator, the denominator. Yeah, so now we know the instantaneous velocity will be the slope of the tangent line will be the limit as h approaches 0. Sometimes they use x, sometimes, or not x, delta x. I'll write that in a second as well, because it depends on your textbook what it's going to look like. Okay, some books write this. Okay, that's a lot of delta x's to use. I like to use h, that way we can see a difference in our variables, because delta x squared, delta x cubed, it gets a little out there, okay? So, and some of you might be in physics or something like that, so this next problem might seem really familiar to you because you might have done it using formulas in physics. We're going to do it with calculus, okay? Given f of t equals negative 4.9 t squared plus 200. Now notice I gave you that that's a position equation. Okay. T is in seconds, and f of t is in meters. Find the velocity when t equals 3. Okay, so basically we have something falling from 200 meters in the air. It's on Earth because of the negative 4.9. The velocity is going to be the instantaneous velocity, right? Which is going to be a derivative. Now, let's go ahead and calculate that, right? So, velocity at t equals 3 will equal the limit as h approaches 0, right, of f of 3 plus h minus f of 3 all over h. Why 3? Well, if you look up here, that's our x value, right? Okay, so the limit as h approaches 0 of negative 4.9 times 3 plus h squared plus 200 minus, all right, handy dandy calculator, negative 4.9 times 3 squared plus 200, negative 42, 180.1. So minus negative, so that'll really be plus all over h. So next line, limit, because we haven't substituted, as h approaches 0, of negative 4.9, 9 plus 6h plus h squared plus 200 plus 42, 180.1, all divided by h. 4.9 times 9. I just realized I did 93. I wondered why that number was so big. Let's adjust that a little. How about 155.9? That's minus 155.9. Don't make typos in your calculator. The limit as h approaches 0 of negative 44.1 minus 29.4h minus 4.9 h squared plus 200 minus 155.9. All divided by h. Now that I have that number correct. Now if you'll notice, this, this, and this add to 0, meaning that they're gone, meaning everything else has an h in it. So now I can do the limit as h approaches 0 of negative 29.4 minus 4.9h, and I can finally substitute 0 and get the velocity is negative 29.4 meters per second. And why is that? Is because y2 minus y1, the y's are in meters, and the time is in seconds. So that's why we have meters per second, is because of the slope. Whew. Now I'm betting in your physics class you just have a formula that you just put it in, and you just do negative 9.8 times t. And there's a reason for that, and we'll get into it eventually. But for now, we're using that formal definition of a limit. And now we get to learn some notation. Okay? So, if they give you f of x as your function, your derivative, okay, you might see it as f prime of x. If they give you y, you might see it y prime, or you might see it as dy over dx, okay? So there's several different ways they can notate it. If you get confused, go ahead and check in the beginning, because there's different notations for different purposes. Some help us better than others. So what is a derivative? Okay, a derivative, remember, it's also the slope of your tangent line. The derivative of position gives you instantaneous velocity. Just remember all that. All those vocabulary words go together, because we're going to know how fast is a particle moving, when does it impact, how fast is it moving upon impact, things like that. Okay, so f derivative of x is going to be the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And I've already told you that for notation and for writing purposes, I prefer the limit as h approaches 0, f of x plus h minus f of x, all divided by h. Okay, so f of x is going to equal 3x squared plus 5x minus 2. Let's find the derivative. Okay, here we go. The limit as h approaches 0 I'm going to use brackets. I have to substitute x plus h the first time, right? So there's my f of x, x plus h substituted, minus, and here we're just f of x. So I kind of use brackets to show the f of x plus h minus f of x. Remember, that's what we're trying to do. So this all needs to be over h. Okay, order of operations, right? Limit as h approaches 0. Now remember, that FOILs out to x squared plus 2xh plus h squared. Distribute. Distribute the negative. and this is all over h. Now we can already see that 5x and 5x will cancel out, and that negative 2 and positive 2 will cancel out. So on my next line, I'm not going to write those down. The limit as h approaches 0 of 3x squared plus 6xh plus 3h squared plus 5h minus 3x squared, all divided by h. And now we can see this cancels out with this. And now we can reduce by a factor of h. So the limit. So it's a good thing your algebra skills are on par for combining like terms, right? We would have 6x because the h would cancel plus 3h plus 5. Now I can finally substitute 0 for h, and I find out that the derivative is just 6x plus 5. Okay? Now I could get the slope of the tangent line if I knew what my x value was, but I was not given an x value. So if you have to do several tangent lines, instead of like before where I put the 3 in at the beginning and worked it out, I could have done it like this right here with all variables and put the 3 in at the end. So right here, I could have went ahead and just did x and worked my way through, and then substituted 3 at the end. That's what I would do if I had multiple slopes I was finding, if I needed the velocity in multiple places. Okay? And there's a relationship between lots of this stuff, so we're going to keep building as we talk about this. So it's really important that you understand where these numbers are coming from and that this is just an average velocity. Okay, so just so I can prove this to you, physics meets calculus. Okay, a lot of you on your physics formula sheet probably have the following formula for position, okay, x equals x sub 0 plus v sub x0 t plus 1/2 a sub x t squared. And then you probably have velocity equals v x sub 0 plus a sub x t. Okay, if you're a person who gets blinded by variables, be very careful here. So I'm going to go ahead and make a t-chart first, okay? I will have x, and I will have x plus h. So this is x sub 0, v sub x sub 0, x plus 1/2 a sub x, x squared. This would be x sub 0 plus v sub x sub 0, x plus h, plus 1/2 a sub x, x plus h squared. So you'll notice that I put in the x and the x plus h for the respective t's here. Okay, now I'm going to do my limit process, right? The limit as h approaches 0. X sub 0, I'm going to go ahead and distribute this. X times v sub x sub 0 plus h times v x sub 0 plus 1/2 a sub x, x squared plus 2xh plus h squared. That's FOILed out. All of that would be subtracting x sub 0 plus x times v sub x0 plus 1/2 a sub x, x squared. We went off the screen. I almost went off the page. All over h. The limit as h approaches 0. x sub 0 plus x v sub x 0 plus h v x sub 0 plus 1/2 ax times x squared plus 1/2 times that is 1, so we'd have a sub x times h plus 1/2 a sub x h squared minus x sub 0 minus x times v sub x 0 minus 1/2 a sub x x squared all over h. Okay, x sub 0 minus x sub 0, xv 0, xv 0, 1/2 ax squared, 1/2 ax squared. Everything now has a factor of h in it. So the limit as h approaches 0 of v x sub 0 plus ax times x plus 1/2 a sub x h. And when I finally put h in, v x sub 0 plus a sub x times x, because that goes away. Let's look back up here. The only difference between these two equations is I've substituted an x. They have a t. So we just took a very complicated position formula, we applied the limit rules, and we got that same velocity. They're related. I think this is really fun. So let's look at area equals pi r squared. Okay? This is just neat to me. So we've got r, and we've got pi r squared, r plus h, so pi r plus h squared, right? The limit as h approaches 0 of pi times r squared plus 2rh plus h squared minus pi r squared. I went ahead and FOILed that out. All over h is the limit as h approaches 0 of pi r squared plus 2 pi rh plus pi h squared minus pi r squared all over h. Cancel, cancel, and then we're going to factor in h out of everything. The limit as h approaches 0 of 2 pi r plus pi h. When h is 0, we get 2 pi r. We started with area, and we ended with circumference. You will find that this derivative process relates a lot of formulas that you've just been given in other places. So that is something that I think is kind of really neat and interesting. We are going to have to do some manipulating sometimes with this, okay? So let's keep going. We did some couple off-the-wall things here, but we've got to keep going. We've got to make sure we know what's going on. Let's find out what happens when we get a radical. In fact, we are going to carry on with this past just getting the derivative. That way, we're going to find the derivative, and we're going to get the equation of the tangent line. When x equals 12. So not only are we going to find the derivative, we're going to come back after we found the derivative, and we're going to get the equation of the tangent line. Okay, so how exactly did I do some of the stuff in my calculator earlier, right? And my window. Okay, so I've got my graph here, and we know we're going to be out here at 12, or the ordered pair 12, 4. I'm going to go ahead and note that down, but that's going to be our point of tangency. That's going to be a big play, okay? And here's why. How do I get the equation of a line? Well, the equation of a line is y minus y1 equals your slope x minus x1, right? We have a y1 and a y and an x1. So y minus 4 equals some kind of slope x minus 12. Once we have that, we're going to have our equation of our tangent line. It's going to pop out. I need to get the slope of my tangent line, and in order to get the slope of my tangent line, I've got to derive. Okay. The limit, remember your derivative, is going to equal the limit as h approaches 0 of your equation with x plus h substituted minus your equation all over h. Well, there's not much we could do there now, is there? So what are we going to do? Well, we've got to get creative. So this has a nice perfect denominator and a really wacky numerator. Normally we always rationalize the denominator, but today we're going to rationalize the numerator. So just like back whenever you were doing rationalizing, you're going to multiply by the conjugate. Whatever you do at the top, you got to do the bottom. And I'm not going to actually distribute the bottom. I'm only going to multiply the top. And here's why. Quick note and a reminder, if you take a minus b and you multiply it times a plus b, you get a squared minus ab plus b squared. These will cancel out every single time. So instead of actually multiplying all that out, I'm just going to say that we have the limit as h approaches 0. We'd have the first part squared, so that would just be x plus h plus 4 minus the second part squared, which would be x plus 4. And we'd have h multiplied by x plus h plus 4 minus, or no, plus. And I know what you might be thinking, that really didn't do much. That looks worse. Well, let's look at it now. The limit as h approaches 0. In the numerator, the x's will cancel out and the 4's will cancel out. We'll be left with h. And in the denominator, we have h but now the h's cancel out. And we have the limit as h approaches 0 of 1 over x plus h plus 4 plus x plus 4. Now when I substitute in 0 for h, I get x plus 4 plus x plus 4, which is boom. Now I have my derivative. Okay, so my derivative's finally done. But to do that problem earlier, I needed to do the slope of my tangent line. And right now I have this going on. Y minus 4 equals, we don't know, x minus 12. That right there needs to be the slope of your tangent line at x equals 12, because that's our x value. Oh, well, come up here. 1 over 2 square root of 12 plus 4. Well, 12 plus 4 is 16. Square root of 16 is 4. 4 times 2 is 8. 1/8. So y would equal 1/8 x minus 12 plus 4. Let's check it out before we simplify it. plus 4, right? Nope, minus 12. And then plus 4. Yep, we found and. They have a point of tangency. If you were to distribute and combine like terms, you'd find out that this is 1/8 x plus 5/2. So getting the equation of the tangent line is a matter of using point-slope form. If you don't understand how to use point-slope form, please go back to my algebra videos and find the one on point-slope form, because we're going to use it a lot in these calculus videos, and so it just becomes a truly spectacular thing to do. You can, party trick if you wanted to, you can use this to approximate. Okay, now that we've done this, right, we have f of x equals square root of x plus 4. And we found the slope of the tangent line, not just the slope, the equation of the tangent line at x equals 12 was y equals 1/8 x plus 5/2. So without a calculator, could you find f of 16? Well, here we'd have to do the square root of 16 plus 4. That would be the square root of 20. Well, that's somewhere between 4 and 5, right? But if we come over here to the tangent line, it will be approximately 1/8 times our x value plus 5/2 is 2.5. So 2 plus 2.5 is 4.5. Let's check. $4.47. We weren't that far off. Could we have done it for 18? Or for, let's do f of 17. Okay, that would be root 21, right? Over here, we'd have 1/8 times 17 plus 2.5. Let's check to see if they're close. Here's root 21. 1/8 times 17 plus 2.5. They're both around 4.6. They're not too far off. Now, the further you get away from 12, the less accurate this becomes. The closer you are to 12, the more accurate it becomes. So we can, if we cannot calculate this because we are having some kind of obstruction, we can approximate it with the equation of a tangent line. So that's another cool effect. Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? And drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.